Perfect. There we go. So we're going to start by previewing the NGSS standards for this unit, and then also take a look through the unit outline and teacher walkthrough. We're not going to spend a lot of time on those, but just giving you the broad overview. Christy's going to talk through task sets 1 and 2. We're going to do a thing together with task set 3, which is going to be a breakout room discussion with the like paradigm lab or main lab for this unit. And then Christy and I are each going to preview task sets 4 and 5, and then also look at the unit assessment examples and rubric. So we have a lot to do today.
So we're pretty excited to show off the new website. So I just want to take a minute, and like Matt said, we do have a ton of stuff to talk about, so not too long on this section, but I just wanted to show you really quickly what our new website looks like. It's very exciting. You'll see the new address up here, highschoolscienceforall.org, and then /chemistry gets us to the new site. And then as we move down, you'll see all the different units are here, right? And then here are some of our, these are the same for all courses. So the NGSS standards, what our design principles are, FAQs, authors and acknowledgement. These are the kind of things that cross all the courses. But for example, if we scroll down here and we look at Unit 6, Stoichiometry, and we click on Unit Materials, notice now that there's a lot more on the page itself, as opposed to so many just going straight to the unit planner, for example. So we have the outcome, the phenomena, the essential question, how's it structured? So here's the overview that we have, and we have an overview for each of our units, and it just kind of gives the big picture and the general flow between the task sets. And then, of course, this is the actual planner itself, which you're all very familiar with. And then the resources are now down a little ways. These resources are also on the unit planner, but they're instead of having to go into the unit planner to get to the rubric, for example, you can get to it straight from the web page. Vocab list. If you want to go straight to the Google folder itself where all of the files are, that's there. The INB is there. And then we have some drop-down things here for how can I do extensions with my students? How will I know if my students have learned things? What are some possible assessments? We just have this one, the unit test right now, etc. Then we have our, our SEPs. What SEPs are we working on? So if you want to dig in a little bit more to the NGSS side, all of that is here. So our website is considered live now. Biology's website is live also. I think physics is maybe still in the works. Let's see if it is. Oh, nope, there it is. So I'm wrong. It's very new is my point. So all of our new pages are here. We're really excited about it. Still doing some little tiny tweaks and updates, but it is here. Already talked about this. Just a reminder also about our open access and our restricted access. So the open access has everything in a file system that's available to anyone with the link. So anyone could go to the unit plan and click on many of those links, and they're all located in the open access. The restricted access, we keep those under lock and key. Those are for teachers' eyes only. So we get a little bit particular about who has access to that, meaning we just want to confirm that you are a teacher, and then of course you have access, and it's got like the teacher notes and the answer keys, assessments, things like that we don't want to have in student hands. And so if you are not able to get into teacher notes, there's one of two things going on. Either you don't have access to the restricted folder, and if that's the case, go ahead and click on this Google form right here and fill out the short Google form. And then within usually a week or so, I go in and look at the new Google form entries, verify that people are teachers, and then give access. If you have already filled out the Google form and have had access, The other issue is that last summer we moved the files to a new location, and an email was sent out, but it might have gone to your junk folder. It might just be something that you overlooked. So here's a screenshot of how to get to it. So it's in now the shared drives, and you'll see it's called Patterns PDX STEM, Patterns Chemistry. There's the open access and there's the restricted access. So those are the two file names that you're wanting to look for. So if you already have access, you know you have access because you've been there before. Chances are you're just not looking in the right spot, and that's because they've been moved and they're in the shared drives now. Questions about that? Anything that I can answer about that? Or Matt, if anything shows up in the chat, just stop me and we'll talk about it.
Great. Okay, yeah, this part's me. I'm going to do this relatively quickly. I'm not going to read all that's on the slide, but the standard for this is HSPS 1-7. This is the chemical reactions standard. And Unit 5, which is about, it's maybe I will read just the first part. Use mathematical representations to support the claim that atoms and therefore mass are conserved during a chemical reaction. From the big picture of this really fits very well with Unit 5, which is chemical reactions, knowing the types, understanding how to balance equations, and then how that relates to the conservation of mass. And so at first pass, this looks like where is stoichiometry in here? And then can you go to the next slide, Christy? If we dig further into the evidence statements, this is where it becomes clear that this is also where the stoichiometry lies. So the evidence statements include identifying the quantities of reactants and products in terms of atoms, moles, mass, molar mass, and the balanced chemical equations, and then doing calculations to convert between those. And so based on whatever you're given if you're given a certain amount of a reactant, how much product would be formed or vice versa. Yeah, so I think I'll just say that that's kind of where this goes. Most of our units, it's pretty clear from the very first, like the first line, like how it fits in. And then this is, you kind of dig a little bit deeper to see like that's where this fits. So yeah, go ahead and go to the next one. And then a big picture overview. The learning target for this unit is to use mathematics and computational thinking to show that atoms and mass are conserved during chemical reactions. That's like the language from the NGSS standards. Our anchoring phenomena, there's kind of two parts. We're going to be thinking of this first stoichiometry as a big picture is used by industrial engineers and chemical engineers to figure out how much of the stuff that you mix together, the reactants, do you need to maximize products and minimize waste. And so throughout the unit, students will be thinking about a wide variety of different chemical reactions. But then we're also going to focus on one specific example, and that's going to be how do engineers know how much material to use to fill a car's airbag? And we'll talk about that in a few minutes. Yeah, I think go ahead. We'll keep going.
So this graphic just gives us a little bit of a roadmap about how the task sets link together. So we're starting always with our opener, trying to activate prior knowledge, generate interest in the topic, introduce the phenomenon, and ultimately connect it to our engineering project. So we're starting with airbag. Well, we're starting at looking at ways stoichiometry is used in everyday life. And then introducing the idea of an airbag, and then thinking about like what are all the pieces that we have to know in order to understand how to inflate an airbag or how an airbag inflates. So we need to do some work on moles. We need to do some work on mole ratios. We need to put those together and do some work on the literal calculation of amounts in stoichiometry. And then we can move to engineering our airbag. So that's kind of the process as we go through the unit. And when we look at the first task set 1, always the unit opener, we're looking at the essential question, like why do we do stoichiometry? What even is it, and why do we do it? And really, it comes down to ratios. So there's this great book I just wanted to point out. It's all the ways that ratios are used in our everyday lives, the simple codes behind the craft of everyday cooking. So highly focused on cooking. but thinking about every recipe as like a ratio of ingredients, literally what stoichiometry is, right? A ratio of ingredients or reactants. So you could really put anything here. There happens to be bread here. I think there was s'mores before on our previous example, but just understanding how does the ratio of these impact the amount of product that we can make, and always trying to go for the best ratio, meaning the least amount of reactants for the most amount of product, and I don't want to have anything left over. So we start with our opener. So I'm just going to look at the slideshow here. So we did a couple of changes on our slideshow for Unit 6. This first part is not a change, where we're looking at different examples of how stoichiometry is used. So we're looking, for example, at agriculture and the role of fertilizer in growing plants, and that's very much a ratio. What's in the fertilizer is a ratio. We're looking at construction, plaster, cement, there's a ratio there. Perfumes, there's a ratio of ingredients there. Rocketry, very important ratios there. Healthcare, a lot of ratios there. Environmental, of course, cooking, internal combustion engine. So you can see there's just many examples here, and hopefully we tried to get a good range. At least one of these should click with every kid, hopefully. And then we get into the airbag piece. So we have, see, we have a couple comments there that we need to finish up, but just there's a video here about how an airbag inflates, just a visual of it. And what's most remarkable about this video, I don't know if you are familiar with the slow-mo guys, but they do a lot of really good videos. So they inflate the airbags in slow motion, but when you run it at regular speed, how quickly the airbag inflates is very remarkable. So something to notice. Also, there's been quite a bit in the news. It says since 2016, but I'm still seeing things about airbag recalls and just some of the issues around what's causing this shrapnel really to be projected from the airbag during inflation. There's a little video there about it. And then we get into talking about this idea of building in a model. So we do a lot of modeling in chemistry, right? But we're bringing the model all the way to the very front of the unit in the unit opener. So that's the first chance that kids really have to try to make sense of what's happening inside that big balloon as it inflates. And how is it inflating so fast? And like literally, what are the particles doing inside that's causing it to inflate? So we're at a very sort of guess and speculate level here because we have had no instruction, right? So I'm hoping for my students, I'm hoping to see some particle level information. I'm thinking back to Unit 1 and KMT when we did gas laws, and we drew lots of models there, right? And we have arrows on our little dots showing direction and how fast it's moving. I'm hoping to see that with my student models here. Because we've done that. We've had that instruction. Might need a reminder, right? But particle level information, I want to see something about pressure here. Notice I did not use that word pressure in my directions, but I'd like to see something about pressure, which is involved in the actual inflation, right? Pushing on the walls of the container. Maybe where are the particles coming from? And again, it's kind of like a wild guess. Like students might be thinking, I have literally no idea where this is coming from. Totally fine, right? You may not have any idea. Just, just put some ideas together. What might be happening? We want to have a starting place to build from as we learn information, and then we come back to our model, we adjust it, we correct it, we add information to it, and we're going to do that all the way through our unit. We're going to sense make as we add information. This is a great way to use our information for our driving question board, right? We come up with questions. After we draw our model, we may have some questions, which is kind of a natural segue to our driving question board, which then when we have students post those questions and we group them, we see that we have kind of categories of questions. People are wondering kind of similar things, and then that helps us drive our instruction. Well, what's causing the inflation? Well, it's probably a gas. Where's the gas coming from? Okay, that's something that we need to know. I'm anticipating a lot of students would have that question, right? Like, what is it coming up the steering column? Where's that even coming from? So I really love doing driving question boards. If you were with me in other unit webinars, you know I love those. I talk about them a lot. It's a great way for students to generate and have some ownership of their learning. Um, Students, I think by nature are a curious people. And so just giving the invitation, the room to ask questions, to wonder, to be curious, um, just inviting that and fostering that, I think is a really important part of being a scientist. And so this is a great way to do that. And then I love this part as we go through the unit, we do check-ins again with our driving question board. Oh my gosh, we know the answer to this. Like it's a celebration. Like, you guys, we know this now. Can someone summarize it for us? And then we put it in our answered bucket. Answered that, right? And it's just it's so satisfying in a way. And it's also very validating for students. Like, cool, I had a question and we learned about it and now I know, right? And that is just also reinforced with our revisiting of our model as we go through the unit. All right, so that's kind of the unit opener. All right, airbag.
Yeah, and this I just copied the same this is the same slide that you already explained. So this is like the students creating their initial model. So we can keep going. And driving question board. Yep.
Yep, and I just stole all the thunder from our couple of slides here about, sorry about that, about model and driving question board. I get really excited when I talk about driving question boards because they're super great. If you have not tried it, highly recommend. Um, And yes, I already sort of talked about these. We have more notes in our resources about driving question boards. So if you want to dig in a little bit more on maybe some specifics for with how to go about that, or how do we get students to write good questions and not like, what is an airbag? Like that's a Googleable question. We're not writing any Googleable questions, right? So how do we train students to write good questions? We have some more information in our resources section. All right, so at the end of Unit 1, we should be familiar with lots of ways that stoichiometry shows up in our everyday life. And really, it comes back to it's all about the ratios. And we're always trying to get the ratio just right so that we can maximize our product, make the most possible product with the least amount of waste. I always put a little business spin on it too. Like imagine you're in a business and you're about making the profit, right? And if you're if you are interested in maximizing your profit, you don't want to have stuff that you're wasting. You don't want to use more than you need to. You don't want to buy more than you need to. And you want to make a lot of the good stuff at the end, right? You want to make a lot of that product. So sometimes when you put it in a business model framework, like that resonates with some kids. So that's what we mean when we say the best ratio. And then we get into task set 2, where we start digging into, okay, great, we know something inflates the bag. We got to figure out what that is. In order to figure out what that is and understand that process, we need to know about something called moles and molar mass. So how do we count atoms? And atoms and molecules are really small, so we tend to have a lot of them. So we have a word that means a number, and that's called a mole. And I usually do a whole thing around mole in my classroom. We have Mole Day that we celebrate in October. It's a big thing. Um, just to try to make it fun because, this unit can be very mathy and it can be very dry. And so just trying to make it highly relevant and engaging so that students, want to dig in and learn. All right.
Cool. And the next couple are going to be mine. So this, by the way, the working on or having students develop the airbag model throughout the course of the unit. This is something new we're trying this year, and it's part of the learning that we're doing together with the councils. We meet anyway on Saturdays, roughly quarterly, and so here's at the start of task set 2, students get their first pieces of information to add to their airbag model. And so like as we go, we're going to either be providing information or students will know or have learned how to figure out the next steps. So it turns out in most airbags, the most common, it's actually a chemical reaction that produces nitrogen gas. And it's a chemical called sodium, or a compound called sodium azide, NaN3, that decomposes when it's heated with electricity. And it decomposes into sodium, metal, and nitrogen gas. And I didn't know this. I didn't know this was what happened. I thought it was probably some sort of like compressed air cartridge that was being opened. And so it's pretty interesting that a chemical reaction could be fast enough to do that. And sodium azide is a white crystalline solid. And so I think if actually this is animated, Christy, so we can click on the next couple things. The model on the right, if you click, I think it'll, yeah, click on the slide, it's going to pop some stuff up. We can just kind of go that. So the model on the right is something that it's a handout that you can print and give to students and that they can add to throughout the course of what we've done. So it might be hard to see, but the diagram has an example of like one formula unit or one molecule of sodium azide, and then one N2 molecule, one nitrogen gas molecule, and then a little sodium. There's sodium metal that's also a product of this reaction that's at the bottom. And then students can add that information. What is it that fills the airbag? It's nitrogen gas. And then write the chemical reaction unbalanced, and then also like a description of what's happening. And then go ahead and move on to the next one. And then so now that we have that information, one of our next questions is, well, how much of the material do engineers use? And it turns out approximately 130 grams of sodium azide is used in a typical airbag in the driver's side. It's different for the different size airbags. And so today in task set 2, we're going to be answering the question, how many molecules of sodium azide is this? And then just quickly, it's an ionic compound, so the proper term is a formula unit. In my classes, I'll say molecules, 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 and then mention formula unit, but I think at this level, thinking of that group, the smallest ratio as a molecule is very appropriate.
Then in task set 2, we are also using, we have some slides here for students to help them conceptualize what a mole is. That's a struggle sometimes just because it's an insanely huge number, right? And so I usually do some mole analogies with them. There's lots on the internet, like how many if you have a mole of donuts and you stack them, like how many trips to the moon and back would that be? That kind of thing, just so they can get a visual, some kind of visual of how much it is. And it turns out it's a crazy huge number, right? So I get a lot of oohs and ahs when I share analogies with them. This video has some at the end, some great analogies. If I had a mole of dollars, like how long it would take me to spend a mole of dollars. So it's fun. It's fun. It's a good, short, engaging video. And then we want to focus on finding molar mass. I don't want to do that. Stop. Okay. And then we're going through and doing basically one-step conversion. So thinking about dimensional analysis, really what this is. And so I do a lot of visuals with my students. If I have something on the top and something on the bottom, they're going to cancel out. So sometimes I even use colors here. So I have like magnetized things that I put on the whiteboard. So before I even use words for units, I'll just put a red thing here. Oh, I want to get rid of that red thing. How do I do that? Oh, I have to put a red thing down here. So I do it very color wise. And then we just get used to seeing top, bottom, top, bottom, top, bottom. Just that it's a little bit of a algorithmic thing that I'm trying to teach them, a stepwise thing. And then I also talk about like I literally use this process is still in my everyday life, even not related to chemistry. Just if I'm trying to do some conversion, I'm at Home Depot and I'm trying to figure out how many bags, how many cubic feet of something I need to buy, right? Of like fertilizer or whatever. And I know that I have this much area in my lawn. So, like, there are so many examples of using this skill because sometimes people say that, when will I ever use this? Well, actually, a lot. Turns out you'll use it a lot. So I start with just colors and thinking about canceling. And then we move into well, I have moles and I'm trying to get to atoms. And sometimes I use the visual that was on the first slide of test set 2, which has mole in the middle and then like molecules and grams and liters, right? And just that's another visual way for, well, I'm here and I want to get here. Oh, look, I have to go through moles first, right? So what is that conversion right there? And just kind of helping them get an idea of how to set things up. Then ultimately, we transition to the phenomenon of the unit, which is more about your car. So we have an activity here that's has all the things that a car is made of, and then we can start to do some conversions. Well, how many atoms is that? How many atoms of iron or is your car made of? Or how many grams is that, etc. Excuse me. So here's that example. So we have the amount of aluminum found in your card. We can figure out how many moles that is. We can figure out how many atoms that is. This happens to be a two-step problem. And then we set up a continuum here so we get kind of a perspective of how much is that, like when we compare the values to each other. So that helps them get sort of a relative perspective. All right. There we go. Or in task set 2, you can also do this activity instead. So instead of doing the car and the practice, kind of the practice calculations, um, after the learning about moles and doing a one-step conversion, there's an inquiry activity where they have a white powder that's in a bag, and their job is to figure out the identity of the white powder. And they have some information that they're given and they have some materials that they're given. Um, and then there's slides that go with it. And again, their job is to figure out what's the identity of the compound. So here's some student examples that I pulled from my classroom. So I set it up just like a CER. So their claim is their answer, like what is the compound? What evidence did you gather to support your claim, and what does that evidence even mean? So what you've done these calculations, how does that even relate to identifying the compound? So a couple of examples. I didn't have them write up a formal CER. We did this as a group. You could, right? You could turn it into a summative assignment. I think we did a formatively just as a practice, but since it was a group, there was lots of student talk. They get to check their answer at the end, so there was some like motivation to see if they did it the right way or they got the right answer, etc. So it was fun. All right.
Yeah. So, and then just revisiting or connecting to that. So if you choose, I recommend the option of like choosing, figuring out what's the substance in the bag. And the substances are, things like sugar or baking soda or, white powders that are harmless. And then we're going to revisit the very end. Let's think back to our example of sodium azide. And just the connection is it's also a white powder. And we learned earlier when we added to our model that about 130 grams is the typical amount used in the driver's side airbag. And so now we can revisit this question, how many molecules is this? And so this is their like exit ticket, their last question for that lesson. And then either at the end of the lesson or at the start of the next lesson, we're going to be adding that information. And so I know you can't probably see zoomed in very well here, but this would be it. You know, they go through figuring out the molar mass of that, and then how many molecules or formula units is that. So we're kind of like adding to our model as we go.
And our takeaways here are, again, atoms are super small. And if we want to figure out how much stuff we have to use some conversion factors to help us get there. We learned about the mole as our central conversion factor and how to use the mole to get us to molar mass, to get us just to grams, to get us just to molecules, etc. And in a later task set, we'll work on putting those together into one larger problem. But those are kind of our takeaways for task set 2. And also, I would say this bullet point, the molar mass of any element or compound is unique and is we can use that information to determine the identity, which is the point of the white powder in a bag, right? We're using molar mass as the identifier for the compound.
All right. I think, can you unshare, Christy? And then I'm going to
Yes.
take over at this point. And we're doing great. We're hoping to start this next activity at 4:45. We said 4:40 to 4:45. So we're kind of right on time. So I have a couple slides I'm going to use to introduce it. And then this is the breakout room part that you'll be doing with others. And let me make sure I get to the right screen. Got it. Okay. You're kind of seeing all my stuff, but that's good. Okay. So task set 3 is about mole ratios. Our essential question is, what's the best ratio? The phenomenon we're using is baking soda and vinegar, so something pretty common. And then it's also cool how it connects again to the airbag, that there's a gas, CO2, that's produced. This could be this could be a way of filling a bag. It's not what's used in real airbags, so just kind of the connection to that. So the next thing for our model, the story so far is we've learned that airbags are inflated with nitrogen gas. It's created when sodium azide is decomposed. Approximately 130 grams of sodium azide is used, which is about 1.2 times 10 to the 24 molecules. It's basically 2 moles, interestingly enough. And so our next question is, how many molecules of nitrogen gas are produced for every molecule of NaN3? And maybe just kind of thinking back to our big question is, how do engineers know how much stuff to use to fill the airbag? That's where we're heading next. Okay, so this next thing, and actually maybe Christy, can you put this link in the chat? We're gonna send you, well, first I'm gonna preview how we do this, or a way of doing this lab. We're calling it the mole ratio lab. And so the information and then also what you'll be doing in teams are in the slide, or sorry, in that link where it says click on the link to access. Perfect. Thank you, Christy. So if you can all go there, and then I'm going to go there as well. Did I get to the right place? Wrong place. Okay. Going through all my tabs. Let me click on the right link. Awesome. All right. And if you were in the Unit 5 webinar, we did something similar to this where we previewed something in an interactive activity, and then you worked with colleagues in a breakout room. Perfect. Great. I'm just kind of hanging on to see if we can get a few more of us here. So again, the link that Christy just put in the chat, that's what you'll need for this next activity. Awesome. Okay, and let me share this screen. So the first few slides, I'm going to describe a way of doing this lab. Yeah, and then you will be accessing data that my students in my classes collected last year, graphing that data in Desmos, and then creating an argument. So creating a digital whiteboard to answer a question. So this is called our mole ratio inquiry lab, and our question is, what's the best ratio of baking soda to vinegar in order to maximize the amount of product, in this case CO2 gas, while minimizing the amount of waste, which would be leftover baking soda or leftover vinegar. And what I'd like to do next is I'm going to talk through a video just showing a way of doing this experiment. When I've done this in class, we did this, we physically demonstrated the experiment, and then also had this video on the slide so we can go back through what to do. And so I'll kind of get to do that talking through part with no volume. So that Erlenmeyer flask has a certain amount of baking soda. In this lab, each team, at least the way that I've done this, each team is going to have a different amount of baking soda. So that's something that your teams will calculate and figure out, and it'll be different from team to team. And then the next thing you're going to see is vinegar. We're using 6 milliliters. We'll explain that in a minute. That'll be the same for everyone. And then what we're seeing is there's a tube connected to a rubber stopper. The rubber stopper is going to be used to plug and then help capture the CO2 gas that's produced. And then the other end of that tube, this teacher is holding his thumb over the end of the tube. He's going to bring it underneath that graduated cylinder. And then once there's gas that's captured, it's going to bubble up. And this is a point where I should mention that graduated cylinder is already filled with water. At this point in class, my students have already done an electrolysis experiment where they have submerged the tube, bloop, 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 get the air bubbles out, submerge it, or keep the end submerged. So that's full with water, and then we can use it to capture the CO2 that's produced. And here we go, holding the end. There's the vinegar in with the baking soda, capping it, and then you can see pretty quickly that gas is produced. And the teacher holding that moved their thumb away from the tube. There's still bubbles being produced, but it seems to be slowing down. The other teacher is going to swirl the contents of that container just to make sure that everything mixes. Yeah, pointing at that's the water level right there. Make sure you hold on to that tube. There you go. And so once the reaction is like complete, there's a couple things that we are going to notice. One is we'll measure the volume of CO2 that was captured in that tube. Since it's a graduated cylinder, you can just read the water level, and it's also upside down. So as it fills up, it's recording the right amount. And then the other thing, I'm not sure if we did it in this video, but I'll explain, is we're also going to use an acid-base indicator in the baking soda and vinegar mixture to find out if there was a leftovers of either. Okay, great. I think here we go. So next slide, just real briefly, these are slides that we use to students to introduce what's baking soda made out of. It's an ionic compound called sodium bicarbonate. I'll just do this quickly. And then what's vinegar made out of? Vinegar is actually about 5% acetic acid. So really this reaction is acetic acid and baking soda. We will often say baking soda and vinegar, but it's a shorthand way of saying it's acetic acid reacting with baking soda. And so for everyone in this experiment, everyone's going to use the same amount of vinegar, 6 milliliters, which turns out to be about 0.0050 moles. And then each team is going to use a different amount of baking soda so that it'll have a different ratio. Okay, and then also just a quick overview of bromothymol blue. This works really well for this experiment. If the end product is acidic, it'll be yellow. If it's basic, it'll be blue. And if it's basic or alkaline, and if it's neutral, it'll be green. So we can tell if there's leftover of acetic acid or of baking soda, or if there was not leftovers of either. Okay, so what I'm going to do next is we'll send you the breakout rooms, but I'd like to preview the work that we're going to have you do. And we have about 30 minutes for this part. So there's some structure here, kind of like last time if you were here in Unit 5. The first thing when you get there, if you're able to share your screen or show your screen so you can see each other and talk, we'd like you to start by just introducing yourself to your team members. So there's some example prompts of things that you might share. Nothing to write on that slide. And then after introducing yourself, consider having one team member share your screen for the next activities. That's especially helpful if there's someone accessing this in your team from their phone. We found it makes the working together, that person will be able to view more of what's happening usually if you're able to do that. And then part 1, there's a wild guess, and this is connected to the airbag example. I'll have you read this wild guess, and then would each of you write your name and then your answer and then your reasoning. And let's keep that pretty quick, but you're guessing, in this case, it's going to say, it turns out roughly 3 moles of nitrogen gas are needed to fill the driver's side airbag in most cars. How many moles of sodium azide would that be, or would be needed to do that? Okay, the next part, data. So it says access the data table, and I would like to show this. The data table that I've used for this lab is something that each will share with the whole class as an editable file, and then each team is doing their own experiment. So we're having you skip the calculations, but students will be given a specific ratio of baking soda to vinegar. Since we're all using the same amount of vinegar, that means they figure out how many moles of baking soda they'll use and then calculate the grams. And then me as a teacher, I go around and check that before they do their experiment. And then they're going to put the data from their 3 trials, or in some cases 4. Often the first one, it's hard. There's a lot going on, so it's hard to do, especially the first time. So they'll put that into one specific row in the data table. Depending on what your slide says, you're either going to access data set 1 or data set 2. Those are data sets from different classes, so that we'll have a little bit of variation in this. And then have someone take a screenshot and then put that into the slide. And then there's a place for you to say something that you notice in the data table. So would you have each person share or write something you notice? Next, there is a Desmos template that you can use to create a graph of the data. You're all welcome to do this, or if you kind of want to split up the work and just have one person do that, you're going to be recording the average value of the volume of CO2, and then you're going to be using 2 different sliders to model this with what's called a piecewise continuous function or a piecewise function. And then here's the main discussion. So once you've done that, we'd like you to create a whiteboard, a digital whiteboard, where you're making a claim to answer the investigation question: what's the best ratio of baking soda to vinegar? And maybe just, okay, I'll just say, and then evidence. There's instructions on the left. It says, what evidence from the data table or graph and observations can you make this to support your claim? And so we really want you to use numbers and then also those observations. And the observations are specifically about the color with the bromothymol blue. So was it blue, yellow, or green? And then interpretation, explain why this evidence supports your claim. And then the reasoning, we'd like you to connect this to the equation. So the first step is to balance the chemical equation, and then explain why the balanced chemical equation supports your claim, and explain the relevant science ideas. And there's some vocabulary that we're encouraging you to use. We have students do this on a big whiteboard, just like you're doing digitally. And then if there's more, oh good, there's an optional slide with resources if you want extra. This is like support that I give to students for helping balance the equation in their lab document. And then if there's time, answering the wild guess and some discussion questions. I'm fully aware that in the time we're giving you, there's a good chance you're not going to get to all of it, but some of your teams might. So we're kind of letting there be that for each team. So one more time, once this thing, the link that Christy put in the slides, once you're there, I'm going to send you a breakout room. Find the breakout room that matches your, find the group that matches your breakout room. You can click on a link on slide 6. And we're shooting for teams of roughly 4. Okay, I think I'm going to stop sharing so I have a better view of what to do. And then roughly our time period on this, I think I'm going to say around 25 minutes is kind of our goal. So at like 5:20 or so, I'm going to stop recording. Perfect. Welcome. If you're watching the recording, sorry, I forgot to hit play, but we just recapped the task set 3, and then now we are starting task set 4, which is stoichiometry. So we went to the unit planner, or in our slides, unit planner, task set 4, and the thing that's called stoichiometry intro practice. And so the connection that I want to make for this is that this document is set up as something for students to use as practice. And it's scaffolded. So at the beginning, it gives a lot of supports. And then as they go, more and more of those supports are taken away so that students are doing on their own. And like I said, I want to focus a little bit more on like what are some of like good instructional strategies for this. So I think I'll kind of mostly leave this for you to peruse. But there are different chemical reactions that are going back to our unit opener. So hydrogen gas is sometimes used as a rocket fuel. And so that's the kind of the theme of this very first question. The next question is metabolizing sugar. Am I saying that right? Okay. Okay. But anyway, yeah, there's a better word for that. But okay, metabolizing sugar. There we go. And then there's other, yeah, producing ammonia, which is the main way that we produce fertilizer as a country. It's very energy intensive. So like these are the examples, and then you'll notice that the steps are going to have less and less scaffolding for students as they go through. So they're taking more and more ownership of the process. Okay, I'm going to leave it kind of at that for now. And then after, so, oh gosh, I went back in the wrong place. Let me slow down. Okay, so these slides for stoichiometry are talking through that, like showing the document that we just showed you, and then the slides that go along with that. And I'm skipping on purpose. Okay, so I wanted to add a couple things that are linked in here. They're linked in the slides, and there are just some strategies for how to teach this. And so this also came up. Some of you asked these questions at the very beginning. I'll make this a little bit bigger. But at the very beginning, this is first connecting to task set 2, and then a potential strategy for task set 4, stoichiometry. So when students are first learning how to do unit conversions, we at Springfield High School, got it. We at Springfield High School start by having them use cards. And so this is taking, sorry, we may have both muted. This is taking some of the writing, like the writing barriers out of it, and also having them do something collaborative. So if you want to click on any of those links, the first one has an example of cards that we print out in cardstock in color. And then, sorry about that. And then cards we print out in color. Some starting cards we print out a different color and then hand out for practice. And these examples, I'll share my screen a little bit more largely, are for students to practice with very basic unit conversions, not chemistry related. So this question, for example, starting a marathon is 26.2 miles. How many inches are there in a marathon? It's kind of a random question to answer. Ask maybe feet is interesting, but we start this out are there 1,000,000? Are there 1,000? Are there 10,000? How would you figure that out? And then with this particular activity, students are we use whiteboards a lot, but placing the cards on a whiteboard, and then taking turns with partners doing that, then using a calculator to do that. And then secondly, this also goes with task set 2, but with molar conversions with molar mass, there's another set of cards that students can use for that. So this isn't the full starting with reactants and heading to the product stoichiometry, but this is like for the intermediate steps a little bit more early on. And then another resource that I have here, we often like to do, this is a strategy or a protocol called the take turns protocol. We use this at my school with balancing equations and then with predicting products, and then also here in stoichiometry. And it's a really good strategy if you have multi-step problems or tasks, not something simple, but something where there's like a lot of figuring out. And so I have a couple screenshots of what this looks like here, and then some problem sets that go along with that, the type of things we might. And so this strategy would also go well with the introduction to stoichiometry, the handout that's in the actual patterns materials as well. So just to kind of call that clearly, with a large whiteboard, you'd have 2 partners. Each partner needs a different colored marker. You have partner A hold up their marker, partner B hold up their marker, and then you help structure it the first time through. Partner A, for example, might be writing the chemical equation, partner B counting them, partner A balance, and then partner B check. That's a little different shown on the slide. And then for our conversion factors, for doing stoichiometry from beginning to end, like having the partners do that. This also works, like having the 2 colors helps prevent students, like one student from just taking over. When you go around, you can see the writing in the 2 different colors. And if you see just one color happening, you can help them figure out, like if your partner doesn't know, but you do, you can tell them what to write. Like that's a helpful way that will like help them learn how to do that. Okay. Christy also had added this link for a simulation. I think I'll just leave this here for people to check, but this is an example that connects back well to Unit 5, where students can figure out the type of reaction, they balance an equation. It's a really interactive way of doing that. And then there's a stoichiometry problem where they can check their answer. And so it's another resource for you for practice. Okay, I'm keeping an eye on time, so I think I'm gonna pass it over to Christy for 5, with this saying, like, at the end of this task set, students now can figure out the last step of our question, which is how much or how many liters of nitrogen gas does this process actually produce? And it turns out it's roughly 45 liters. And you'll see, actually coming up with our end of unit assessment, that the airbag itself, most of those airbags need about 70 liters of gas to fill them up. And there's actually a secondary process that happens to add the rest of that nitrogen gas. Okay, are you ready, Chris? I'm going to stop sharing and turn it back over to you.
I am ready. Okay. So now we're at the I'm gonna get a little note here. Yes, keep going. Okay. So now we are to the engineering part of the unit, and this is where we're actually going to be constructing an airbag. So we know, because we've been looking at it multiple times throughout the unit, airbags rapidly fill with gas. We've drawn pictures of that. We have done some calculations to figure out with a certain amount of starting material how much gas is produced in the reaction. We've seen a video about how quickly that happens, etc. So now we're sort of putting it all together with our hands-on piece. So there is an introductory part of the engineering project that has them doing a little bit of background reading, and they're exploring a CK12 simulation where there's actually a couple of reactions happening here. We've been looking at the sodium azide, and then you can change the amount of chemical and press play. Here it is right here. You can see it. And then you can sort of watch what happens. Oops, I cannot do that because it's not live. But anyway, you can go through the CK12 simulation, and they can see sort of the impact of the dummy. They can see the reaction. And again, they've seen all of this, right? So the simulation is nice because they're taking what they've drawn and what we've calculated and what they've thought about, and they're seeing how it would actually play out in a simulation. Okay. So they're looking at they're introduced to the 3 reactions that simultaneously happen during an airbag inflation. And then they look at the type of reaction, they write out the products, they balance them. So we're revisiting Unit 5 a little bit, right? Some opportunity there for another multiple opportunity at Unit 5. And then we're using some stoichiometry to figure out, we're doing some calculations up front. And they're looking also at the second reaction. So Matt alluded to that a little bit in the model drawing, but in the airbag engineering, they actually get to look at it a little bit closer. And then they're coming up with some solutions. So we just use a sandwich bag, like a Ziploc sandwich bag, and we know that that's our airbag and we want to fully inflate it. And so we do some thinking about, okay, how can if I know that's what I want to do, how do I work backwards to figure out how much starting material I should begin with? So we're calling upon the things that we just learned, right? In our model, we did it the other way. We started with a certain amount. We figured out how many liters of gas that produces. Well, now we're going to work the other way. We're going to start with an inflated bag, figure out how much volume that is, and then work backwards and figure out how much reactant we need to do that full inflation. So the first thing that they have to do is figure out what is the max volume of their Ziploc baggie. And I don't give a lot of hints or structure on this one. I want to see what they do. It's a great opportunity to talk about error analysis too. So why are we getting different values? Like if we all have the same size Ziploc baggie, shouldn't we all be getting the same value? So that from that ensues a nice conversation about, oh, well, maybe our techniques are different, or did you take this into account? Well, what about this? Do you have an air bubble? Should we have an air bubble? Things like that. So I let them kind of mess around with that a little bit. Then we pause, then we talk about it, then they go back and they do it a few more times and with hopefully with a refined technique, and then take an average of the volumes that they come up with. And then they do some back calculating to figure out how much starting material do they need. And then they go through the process of actually inflating the baggie. And it's fascinating because there's a range of results, because there's a range of techniques. It's a great opportunity to evaluate error. And why did yours inflate all the way and is like firm, like it's a hard baggy now versus yours is kind of squishy, clearly did not fully inflate. And why are you using different amounts? It's a great opportunity to talk about it. It's a great opportunity to talk about um, procedural error. How are you adding the reactants together in the bag? Because the moment they touch, they begin making a gas. And here you're bumbling around like trying to zip up your bag, right? So it's a it, it's one of the labs that we have this year in the year that does a really nice job of capturing a fairly challenging task of evaluating error. I find that students struggle with that. And there are some obvious errors that are happening here. So it's not hard to identify them. It's more challenging to figure out how are they impacting the results, right? And so it's a great conversation. They do pros and cons for their design. How do we know if it's fully inflated or not? I mean, it looks fully inflated. It feels very firm. Um, is there a way to measure that? I mean, no, we don't really have a quantitative way to measure it. It's more just sort of a qualitative comparison. We've tried some things before, like we tie a string around it and we measure the length of the string and then use that as our data measurement. The other thing that's interesting is that there's some liquid in the bag, and people did not anticipate that. Like, what is this liquid? And that's taking up space, right? And we didn't account for that space. So lots of good conversations come from this. We do it a couple of times. We try to make it better each time, propose solutions, modifications to make it better. And really, then wrapping up, I love the first bullet, stoichiometry can save lives, like literally, right, with an airbag, but also just, I really like for students, for them to see that, it's not like someone just thought someday about, oh, I'll just put this bag in here in the car and like there's a whole thought process to that, and what inflates the bag and how do we figure out what the chemical is and how do we figure out how much chemical and what if it doesn't fully inflate? What if there's a whole, all the pieces that go into it. It's part of that being curious observers in our life, being curious about the world that's around us, and asking questions. That's what I really want them to do as they, go out into the world is to wonder and to be curious. So always coming back to asking questions, wondering. Sometimes we don't know the answer, and that's okay. It's okay to not know. We can still ask questions. We can still wonder. Um, just, I also like to point out to students just how many things they need to know in order to do the work that they just did. Think about all the stuff that we learned in Unit 5 about reactions, all the stuff that we learned in 6. Like at this time of year, we have a considerable amount of chemistry knowledge, and that's something to celebrate. These are hard pieces of information to learn. And not only did you just learn it, but then you applied it to this bigger situation. Like you had a goal, you constructed an airbag, and you used all these pieces of knowledge to do that. And that's cool. That's something worth celebrating, calling out, right? Um, let's see.
I think,
Any,
oh yeah, go
yeah,
ahead.
questions. I was just gonna say, any questions about the airbag before we talk assessment? And how, we're doing okay on time so far. Yay. I don't have my
What
chat open, so if you see any
I do, yeah.
question, okay.
What size do you use, a sandwich size bag or a quart
I,
size bag?
when we were in CDL, we just used whatever bag they had at home, right? So we varied in the other good thing about this lab is that it can be entirely virtual or it can be entirely in person, and you don't really need to do anything different. You don't need to modify the lab in any way to do either one. So I've done it where we all varied the size of the bag, and I've done it where we all have a sandwich bag. So I think you get interesting results either way. Um, so yeah, could do it either way.
Cool. I think let's keep going. I don't
All
see.
right. Do you want to talk about the assessment or do you want me
I
to?
do. Yeah, if you can
Okay, do it.
do you want to
Yep,
let me
yep.
drive?
I do.
I
Stop
will.
share.
Thanks. Let me make sure I'm in the right place. Okay, we're going to do a pretty quick look at this. Why am I having trouble sharing? Uh,
Because it acts like mine is still sharing. Hang on.
okay, no, I got it. I see it now. Thank you.
Cancel. Okay.
We're good. Okay. So Jomi Sika on our team is the one that put these things together for us. So the first thing is the Unit 6 rubric, and it's a document that describes like what are we assessing for and at the level of each of the different tasks. So task set 2, where students are doing well, I'll just read it. They're converting between mass and atoms or molecules using moles as the intermediate. And so that's using molar mass and going from, yeah, mass to moles or moles to atoms. That's task set 2. Task set 3, which is our mole ratio lab. I won't read them, but like these are the different, yeah, the different things that we're assessing in that lab and categorizing them into science and engineering practices, the actual DCIs, the content standards, and then the cross-cutting concepts. Um, our test it for with stoichiometry. This is basically starting with anything as a product and getting to anything as a reactant, mass, volume, number of particles. Our airbag engineering standards, and then also the Unit 6 assessment, which is what we're going to look at. So yeah, I think I've been thankful that she's been creating those this year to see like to help us define what is it that we're trying to assess with each of those. And then the last are end of unit assessment examples. We're calling these assessment examples. It's not necessarily intended that this would be your end of unit assessment, but these are examples that are getting towards proficiency and advanced or mastery. And so this also it works out that the most common reactants used in an airbag actually undergo 3 different chemical processes, 3 different chemical reactions. And so it kind of works out well to give a good variety of things for one particular assessment. And so as you look, there's going to be an example of the first reaction that we looked at. And then, so this one, I'm just re-looking myself. You're given a volume of gas, and then we're going to molecules. So we're going to go from volume to moles to molecules. Yeah, and then this is going from that amount of molecules to mass. Am I saying that right? Yeah, perfect. Good. And then our next good. Oh yeah, and Jenny was saying this is so then this next part is getting more into experimental design. She had her students do this last year and really liked it. This is having students design. So in an actual, like if you actually do this chemical reaction, you can predict how much it would produce, but then you also need to be able to measure like what's your percent yield, but like how much is it actually going to make? And so this next question, number 3, is asking students to draw and write a procedure on how would they measure how much product is actually produced in that reaction. And so that's a cool connection to the airbag engineering task when you were doing that. And then just going through to the next part, this is the next chemical reaction or the secondary chemical reaction that happens. It turns out the sodium metal that is produced as a byproduct in the first chemical reaction can also be used to produce extra nitrogen gas. And it also makes this process safer to not have pure sodium in the airbag. And so is it potassium nitrate is used, reacts with the leftover sodium to make additional nitrogen gas. And so this gives us, in this assessment, a chance for there to be more examples of more and varied stoichiometry for students to do. And then there's a third reactant that is third reaction that's a synthesis reaction that puts together 3 of these products and makes a harmless and stable silicate glass product. And so this one, the question is, you and a fellow chemical engineer are calculating how much SiO2, silicon dioxide, is needed, and your coworker wants you to double check their work. And so your job is to find the mistakes, find as many mistakes as you can in their work, and then say how you would fix it. Awesome. So, Christy, I think we're on to our last couple slides. Would you like to talk through these ones? Is that?
Sure. Yeah, I can do that. We have, we're, getting on near the end of the year now, so we have just a few left. We have one more in chemistry. We have Unit 7, which is our thermochem, and Matt and I will be hosting that again, and that's May 1st. And then we have a Unit 7 for physics, space and the universe, and biology. We have a Unit 5, evolution. So the biology one's coming up next week, and then April for the physics. And then finally, there's our link for the feedback. So if you can take a few minutes, we actually have a few minutes left. We have about 9 minutes left. So if you could take a few minutes to fill that out, we really appreciate it. We look carefully at all of our feedback, always trying to make our webinars better. And there's our contact information. If you ever want to reach out or you have questions, I did see in my email that I have a couple of Google form people who were looking for access to the restricted folder. So that's awesome, assuming that those folks are here tonight. Appreciate you taking a couple hours out on your Wednesday evening to be here. I know that's a big ask after being in the classroom all day. So yep, just appreciate you. Thank you so much for coming, and feel free to hang out if you have any questions. And we look forward to seeing you next time.
Thank you, everyone.
Are these slides, I just saw that, are these slides available after the Zoom meeting? Yes. So if you just keep that link, you can access them whenever you like.
And then also these are in the open access, the PD slides we've been putting in our open access folder. So there's a way for you to navigate to them if there's a folder called PD slides and materials. But you can also just keep the tab open if it's helpful.
Thank you.
Yeah, thank
you're welcome.
you. Thank you. Have a great night. Do you want to stop recording, Matt?
Yes, I do. Thank you for reminding me.
No problem. Hi, Carolee. Do you have Carol Acree? Sorry, I said it wrong. Do you have a question?
No, sorry, I was filling out the
That's
webinar.
perfect.
Oh, you're fine. Yeah, do it.
Yeah,
Yep.
yeah,
Do
I can. Thank you. I appreciate it.
Thank you so much. Thank you.